we're going to go for the discrete time, but we're not going to work with periods of 1 year. We're going to work with periods of a month, for instance, or a semester, or a quarter, or something, right? So what we're going to do is we're going to use with a new random variable, kxm, where the m refers to the number of intervals I'm going to split my year into. So the m, if m is 2, then I work with half years. If m is 4, then I work with trimesters. If m is 12, then I'm working with months, right? So this is the future lifetime of x in years, but it is rounded to the lower 1/n of a year. So that would mean you express it in months, for example. So here is an example of how that goes. So let's say we've got an individual. He or she lives 23.67 years. Then the kx would be 23. That's measured in whole years. That's the floor function applied to this 23.675. If I look at kx with a superscript 2, that's 23.5. If I look at kx with a superscript 4, that's 23.5 as well. And if I look at the months, then I'll get 8 months are survived within this year, right? So that's what we're going to do. It's often a little bit difficult, the 1/mth-ly case. That's difficult for me to pronounce, but I hope you get the intuition. We take a period of 1 year, we split it in m intervals of equal length, and that's the time grid that we're going to use. And why do we do that? Because of course this is coming the closest to reality that we'll probably want to do, because continuous time, that's really, I mean, we cannot manage that in reality. Paying a benefit at the end of the year, that is too slow for our individual. But if we can work with months, for example, then we're good. Then we come in a more realistic setting. So Cas is asking me, why is the k with the 4, so this one, why is it not 23.75? And like Minna said, it's a floor function, right? Cas, so you only want to, like if you look at semesters, you would split the year from 23 to 23.25, 23.5, 23.75, and then 24. But our individual did not reach 23.75, right? So if we work with this curved lifetime, expressed in trimesters, then the part that he survived is 23.5, because he didn't reach the point 23.75. Yeah. So keep in mind here, this is a realistic setting because it allows us to pay pensions at the beginning of the month, to work with months, with quarters, etc. Yeah. So if kxm is equal to k, that means that my individual dies between k and k plus 1/m, because 1/m, that's now the length of the intervals in my time grid. And then you just have to be careful. The k is now, of course, not running over the integers. It is running over the values 0, 1/m, 2/m, 3/m, etc. Yeah, so that's what we mean. So the k runs over all these points in my time grid. So what is my probability function here? My probability function is, what's the probability that kxm is equal to k? That means that your future lifetime, tx, takes a value between k and k plus 1/m. So in between these two time points from your time grid. How can we express this probability? Once again, you need to survive until hx plus k, and then you need to die within, let's say, 1 month or 1 quarter or 1/n year from this time point. Yeah, and we can work with that in the following way. This is also a motivation or a reason why we needed this fractional age assumption from the previous chapter. Because now if we pick up a life table for the Netherlands or for China or for Belgium, and then we can go from the integer ages in the life table to saying something about the probability to survive a couple of months or something with this fractional age assumption. And we need it here in this realistic time grid that we are deploying, that we are introducing over here. Yeah. So if I picture it once again, I like the timeline pictures. So what do? We look at a €1 dead benefit. We look at the case where my individual dies between hx plus k and x plus k plus 1 over m, right? So our timeline is now counting with 1 over m. So 1 over m, 2 over m, 3 over m, etc. If the individual dies within these two time points, then I'll pay my €1 at the time point k plus 1 over m. So if m is 12, that would mean you pay the €1 at the end of the month of death, right? So the discounting goes from this time point to 0, right? So with discount factor expressed like this, and the probability. So what are we doing here? That's my discount factor. What's the probability that this scenario is going to unravel? It means that you're going to survive until hx plus k, and then you'll die within time length 1 over m from this hx plus k on. So again, the probability that this happens is the blue probability multiplied with the purple probability. Okay, so here we are. If the kxm is equal to k, be aware the k runs here over 0, 1 over m, 2 over m, etc. Then the present value random variable takes the value e to the power minus delta multiplied with k plus 1 over m. Yeah? So don't forget the plus 1 over m. That's the same as the k plus 1 that we had in the annual setting, right? We will pay the benefit at the end of the month, at the end of the quarter, at the end of the semester. So putting it all together, if I look at the present value of a €1 benefit payable at the end of the month of debt, then that random variable can be expressed like this. So we have the v to the power kx12 plus 1 over 12, right? If m is 12. And if I calculate the expected value of z, then I'll get the actuarial value or the expected present value of a whole life insurance product with a benefit of €1 that pays out at the end of the month of death, right? And I've got a new or slightly new notation for that. I've got the 12 between brackets as a superscript at the right-hand side of my symbol. So putting it all together, and that concludes the class for today. We need the probability function of my discrete random variable kxm. So we need to know what's the probability that you will die between k and k plus 1 over m. We know how to express that. We know how to use this probability function to value the expected value of a discrete random variable. So if we do that, we arrive at the following valuation form. Yeah, so it's always the same kind of reasoning, but our time grid changes. Essentially our time grid changes, and our distribution may switch from a continuous distribution to a discrete distribution. So that's what we need to keep in mind.